Hello everybody, I'm back again with another video today. I've got a bit of a midterm coming up this upcoming week, and I figured I'd kind of get the ball rolling again by discussing some problems that I myself have gone through for my homework and whatnot, so I can explain things better, and if I can explain it and teach it to you guys maybe, then I can understand it when I'm, taking the exam. It seemed to work okay last time. I will definitely attribute this idea of, this is applied Feynman technique, I guess, for lack of better words, to doing a little bit better in this particular class than in my other one. So for that reason, I'm going to go over some of these problems I've done in my homework. They are from Rife's Thermal and Statistical Physics. I believe I have the book here on me if you guys want to take a gander. It is this one right here. Very good, very handy book, but yeah. And for future reference, I'm going to start doing the same thing with Jackson's electrodynamics as well, so that way I can get better at teaching and doing electromagnetism as well, and understanding electromagnetism. Anyway, enough of that. We have ourselves our first problem. This is 5.1 out of Rife's Thermal and Statistical Physics. And basically we have this ideal gas, which I've just represented as this sphere, and it is temperature independent, it has a temperature independent, molar specific heat C sub V, which means that it's at a constant volume. We're going to define some simple constants being, gamma is equal to the specific heat with constant pressure divided by the specific heat with constant volume. Our gas in this particular setup is thermally isolated, and we can allow it to expand outward quasi-statically, so really, really slow and incrementally until it reaches some final volume with an associated final temperature T sub F. So we are basically asked, with these particular conditions, how do we calculate something like our final temperature? And then in part B, we're asked to do the same thing, but instead of using some sort of idea from the ideal gas law, specifically with adiabatic expansion, to do the same thing with just entropy considerations, right? So if we want to do this with our ideal gas law, we're going to make use of the relationship that P times V to the power of gamma, being the ratio of the specific heat with constant pressure and the specific heat with constant volume, is equal to gamma. That's all equal to some constant, right? So if that's equal to a constant, then we can just set up any sort of incremental change in between the pressure and the volume to be the same, since they're both constant values, right? They have to be. So along any other stage of this thermal expansion in between volume initial to the final volume, we can make this equality, right? So if that's the case, then all that matters is just trying to solve for what our final temperature is. And we know how to get temperature from pressure using the ideal gas law, where we have that pressure is equal to the number of moles of our material times the ideal gas constant R times the temperature divided by the volume. So we just declare two variables, P sub I for our initial pressure, P sub F for our final pressure, and then we stick those two guys back equal to one another. And because we want to solve for our final temperature in terms of our other constants, we make the substitution of Pi and Pf into this equation, right? So we get nu RT sub I divided by Vi times Vi to the power of gamma, same thing on the right-hand side. And then we just algebraically move some terms around, and then we can get a final expression for our final temperature being equal to our initial temperature times the ratio of our initial volume to our final volume to the power of gamma minus 1. Now, a lot of solutions manual, I think the solution manual actually has it to where we have V final over V initial, and then we have 1 minus gamma for our ratio, but either or, it works mathematically, unless I've just fundamentally screwed up my concept of how exponentials work, right? So I'm going to just skedaddle over on the other side so I can point, right? So for the other consideration, we need to look at our idea of entropy, right? So we know that we can write our expression for entropy as being, I forgot to write over T. Whoops. Over T. There we go. We can express our entropy as being the integral of our change in heat, or inexact differential Q divided by T. And then we can make a substitution using our equation for Q into this expression for Q is equal to the molar the mass times the specific heat times the change in temperature, right? So we make that substitution. We want to look at a change in temperature, so we allow the differential to tag itself to our T in our relationship, and then this comes from another equation in Rife itself, but you can essentially write dq as an expansion of nu c dt plus I think RTV. If I remember correctly, I might be misremembering things, but there's an equation in Rife for it, and I'll include it down in the description below so I don't forget, or I'll put a comment, right? So you guys have something specific to reference, and so that I also have something specific to reference a little for later. We do that integration. We have, natural logarithms on both of the integrals. Once we resolve both of these, this is supposed to be a nu. One of these is a nu. My bad, I didn't write that right, but we do have a 1 over v, and that's a nu dv. So we get a natural logarithm in this integral. These aren't v's, they don't cancel out. This one's a nu. My bad. Curse you Greek, and curse myself for not writing it properly. But we know that for entropy, after we do the integration, that our change in entropy always has to be equal to 0. So if that's the case, then all we need to do is just algebraically move these two guys around after we set the left-hand side of our equation of s equal to 0, and then that allows us to exponentiate both sides, and then we can use the the quirky little frog over log rules that we have in like algebra 1 and whatnot. Let's just take this r and then we can raise it to the power over here, right? And same thing with this multi-specific heat. The nus actually cancel out up over here. We want to look at it that way. And then from then on, it's just trying to express this in terms of something similar to what we have down below, right? So we just play around with the exponentials, right? So we'll get like TF divided by TI to the power of CV, and then we'll have our VF over VI expression to the power of negative R. We can flip that around because we know the negative power of something is the same thing as the reciprocal of the positive power of something. We know what R is from the Meyer relation. That is that R is equal to our molar specific heat Cp minus Cv. I believe it's called the Meyer relation. I could be forgetting the name properly, but this is a well-known expression for the ideal gas constant R. Then we can use some tricks like multiplying both sides by 1 over Cv, so we can get this to be to the power of 1, and then we can get an expression for gamma over here on the other side, which is what we need for that final expression over there. And then ultimately, once again, it's just figuring out which ways the exponents work, and we can get a final expression that matches our other one for when we weren't doing the entropy consideration, but rather the ideal gas consideration. So a lot of this problem is strictly just algebra and knowing how to play around with some simple algebraic rules and some logarithms, and knowing properties of entropy, like for a system that it can't change, specifically for an adiabatic one. It's either equal to or greater than equal to 0. And that holds really for anything anyway. That's like the second law of thermodynamics. But yeah, a lot of algebra. If you know algebra, you can solve this kind of problem. And this is what's being taught at grad school level at the moment, apparently. But yeah.